temperature, and kinetic energy. Hold on to your hats, we're going to do a little bit of maths here. What we're trying to do is relate the macroscopic quantity temperature to the kinetic energy of individual gas molecules. That is, a microscopic quantity of the gas. In order to get from one to the other, we're going to have to do some summation. So consider a cube filled with gas. The cube has dimensions L by L by L. So the x direction is across the page, the y direction is in and out of the page, not shown, and the z direction is up and down the page. So instead of the cube, we have a square cross-section in the xz plane. Consider a molecule of gas with a mass m and a velocity v in the x direction. So we'll give it the subscript x, and we're going to label this as the ith molecule. So the velocity is v subscript xi. And so the linear momentum of that particular molecule is p subscript I by equal to the mass by v subscript xi. Because it's an ideal gas, as it undergoes a collision with the wall, it's perfectly elastic and happens instantaneously. So the momentum it has afterwards is simply minus the magnitude that it had before, in this case minus mvxi. And so the particle, or the molecule of air, undergoes a change of momentum, linear momentum, which is twice its initial value, 2 mvxi. And so that molecule transfers a momentum to the wall. And the momentum that it transfers to the wall is, again, delta pi is equal to 2 mvxi. Now, the return time for a collision for that particular molecule is going to be the time it takes to go from the wall it's just hit to the opposite wall and back again. So the distance it has to travel is 2l, and it travels it with its velocity vxi, and so the time it takes to return to the original wall is 2l on vxi. Now, as an exercise, check that that's correct in terms of its units. So we can define force as change in momentum divided by time over which that momentum is imparted. And so the force by the ith particle F subscript I due to this molecule, the ith molecule, is delta pi on delta t. And that's equal to twice the mass by the velocity in the x direction, that's the momentum, divided through by the time, the return time, which is 2l by vxi. And when you invert the fraction on the denominator, you get that the force imparted upon the wall by the ith molecule is mvxi all squared divided through by the length of our box. But we then need to think about what's the total force upon a surface in this wall, rather a surface in this volume, one of the walls. And it's the sum over all the molecules that are travelling in that direction. And so F is equal to the sum of all the F subscript i's. And because the mass is the same for all the molecules, and they all exist in the same box, we can take m on L outside the summation, and you simply have the sum of the vxi all squareds. But we actually got a three-dimensional gas, and so there are gas molecules moving in the x direction, the y direction, and the z direction, and so the sum of all the vi all squareds is equal to the sum of the squareds of the velocities in each direction. But we're going to assume that the gas is isotropic, which is to say that the sum of all the velocities is the same in each direction. And so the sum of the vi all squareds is equal to 3 by the sum of the vxi all squareds. And so we can replace vxi all squared in our summation in the equation at the top to calculate the force on a wall. And so the force on the wall is m on 3l by the sum of vi all squared, the sum of all our velocities squared, or rather the sum of the square of all the velocities. So what we need now is to take this equation for the force on a wall and rewrite it in terms of kinetic energy. So we've got m on 3l by vi all squared, and if we take the m inside the summation and multiply by half, which means we need to multiply by 2, you end up with 2 on 3l by the sum of half m vi all squared, which is the sum of the kinetic energies of all the molecules in the gas. We then divide and multiply by the total number of molecules of gas. And so outside the summation, we've got 2n on 3l, twice the number of molecules divided through by 3 times the length scale. And then if a half mv I all squared summed up is the total kinetic energy of the gas inside the box, if I divide through by the number of molecules, I end up with the mean kinetic energy for the gas. So it's the averaged out value. And so the force on a wall is equal to 2n on 3l by the mean kinetic energy. Now pressure is equal to force per unit area, which is force divided by our length squared, because we've got a box here. And so we can take our equation for force that we've derived in terms of the mean kinetic energy and now write it in terms of the pressure. So the pressure is twice the number of molecules divided by 3 by L cubed, which is the dimensions of our box, by the mean kinetic energy. And because we have a cube, L cubed is the volume. So P is equal to 2n on 3v by the mean kinetic energy. And so if you then multiply both sides of the equation by v, you get PV is 2n on 3 by the mean kinetic energy. This should look quite familiar. PV is the left-hand side of the ideal gas equation, or the equation of state. And so if we use the first form that we saw in a previous video, PV equals nKT, then nKT is equal to 2n on 3 Ke mean, which is the mean kinetic energy. And so once we've cancelled out the number of molecules on both sides of the equation, we end up with the equation that says that the mean kinetic energy is 3 times a half kT. So the mean kinetic energy is proportional to the mean temperature of the gas. Or as it's written there, the temperature is proportional to the mean kinetic energy of molecules in the gas.